Hey guys, this is the last video for the thermochemistry chapter, and we're going to be talking about standard state thermochemical quantities. When you're solving thermochemistry problems, you often make use of thermochemical data. That is, you have to look up thermodynamic quantities for different substances, and this data is tabulated for what are known as standard state conditions in thermochemistry. For our purposes, the standard state will be 1 atmosphere pressure and then some fixed value of temperature. That is, the quantities are tabulated for a particular value of temperature. There's no official standard state temperature, but most thermodynamic tables are tabulated at 25 degrees Celsius. So these are the agreed upon conditions for standard state, and when you go to look up thermodynamic quantities, they are tabulated for these conditions. We denote the standard state conditions by using a little superscript circle when we write down the enthalpy of reaction. So the delta H of reaction with a little circle up above denotes the enthalpy of reaction under standard state conditions, and very often it is implied that this is an intensive quantity. That is, instead of being expressed in terms of just delta H, it's actually expressed in terms of the kilojoules per mole of reaction, okay, which is intensive and doesn't depend on the size of the system. You have to be a little careful with this because some textbooks, they use, sometimes the units are kind of sloppily done. And so sometimes they will mean the extensive version, other times they'll mean the intensive version. You just have to figure it out from the context. But generally speaking, delta H with the circle denotes kilojoules per mole in terms of the energy units used. We also need to talk about the reference form of an element. This is an important aspect of thermochemical equations and thermochemical data. Recall from our previous discussion that elements, which are composed of only one type of atom, can come in different forms, which are called allotropes. Examples are here for oxygen. You could have monoatomic oxygen gas, diatomic oxygen gas, triatomic oxygen gas, which is called ozone. These are all allotropes of oxygen. And under standard state conditions, only one of them is the most stable. In fact, that is the diatomic form of oxygen. And so the term reference form refers to the most stable allotrope of an element under standard state conditions. So the reference form of oxygen, elemental oxygen, is diatomic oxygen gas because it's the most stable of these under standard state conditions. Another example, allotropes of carbon. Graphite and diamond are two allotropes of carbon. And under standard state conditions, the graphite is the most stable form. So the reference form of carbon in thermodynamics is graphite, not diamond. Here are some common reference forms that you should know about, at least this top row and including carbon. You need to know that diatomic hydrogen gas, diatomic nitrogen, diatomic oxygen, diatomic fluorine, and diatomic chlorine gas, these are the reference forms of these elements. For bromine, it's diatomic, but it's the liquid phase that is the reference form. Bromine is a liquid at 1 atmosphere pressure and roughly room temperature. Iodine is also diatomic, but it's a solid. So you have the diatomic molecules are packed together in the solid state. That's the reference form for iodine. You should also know that graphite is the reference form for carbon. You don't have to memorize the reference forms for phosphorus and sulfur. These refer to the type of crystal structure that the molecules are packed into. As we'll learn later on in the course at the end, you can create molecular solids in different, you can pack the molecules together in different ways to form different crystals, different types of crystals. And so these just refer to a specific crystalline form of phosphorus and sulfur, but we don't need to memorize those. However, generally speaking, one would expect a chemistry student to know these particular reference forms. The next topic deals with what are called formation reactions. Okay, so this formation reaction is a specific type of thermochemical equation, and it merits its own enthalpy of reaction, called the enthalpy of formation, this delta H subscript F. So let me explain what a formation reaction is. Every substance, every compound, has a formation reaction. And the formation reaction has the following characteristics. It has exactly 1 mole of that compound as the product and nothing else. Okay, so right away, a formation reaction has 1 mole of product for a particular compound. And then the reactants in the formation reaction are elements in their standard state reference forms. Okay, so you have elements on one side of the equation and then only 1 mole of a compound on the product side of the equation. Each compound has its own formation reaction. I provided a few here. The formation reaction for water vapor. You have hydrogen atoms present in water, so you need hydrogen atoms in the reference form, and the reference form of hydrogen is H2 gas. You have 1 oxygen atom in water, and so you need the reference form of oxygen gas, which is O2. Now, O2 has two atoms of oxygen. You need 1, so you're forced to put a fraction in this formation reaction. And that's okay. Thermochemical equations are allowed to have fractions because we only interpret them at the macroscopic or mole level. In any case, this is the formation reaction for water vapor, and this is the enthalpy of formation for water vapor. The enthalpy of formation for liquid water, similar chemical equation. The phase is different, of course, but you'll see that the enthalpy of formation is a different value. These aren't the same. Here's methanol, liquid methanol. 1 mole of liquid methanol in the products for its formation reaction, and then you want to put the elements in their reference form. So there's 1 carbon, so we're going to have 1 mole of carbon as a solid. This would be graphite. You've got 4 hydrogen atoms, so we have diatomic hydrogen gas, which is the reference form of hydrogen, and we're going to need 2 moles of that to match the 4 moles in the products. We have 1 oxygen atom, so again, O2 is the reference form. We need to divide that by 1/2, so we have the right number of oxygens on each side. And here's the enthalpy of formation for methanol. The circle implies standard state conditions, so delta H of formation is an intensive quantity expressed in units of kilojoules per mole. And I'll point out one more thing, that the enthalpy of formation for elements in their reference forms is by definition 0. For example, if you were to write out the formation reaction for diatomic oxygen gas, you would have O2, 1 mole of O2 as the products, and then in the reactant side, you need to put the reference form of the atoms, or of the element. Well, that's just O2 gas, right? And so the reactants are the same as the products. And so the enthalpy of formation for an element in its reference form is 0. If you were to have monoatomic oxygen gas, however, you would write 1/2 O2 gas. And here, this enthalpy of formation is not going to be 0. In fact, I think it's going to be a positive value. So that's the enthalpy of formation reactions for elements in their reference form. The last conceptual bit here is to apply Hess's law and enthalpies of formation to general reactions. And so, there's a lot of tabulated thermochemical data out there, but we typically don't tabulate the thermochemical values for every possible reaction. There's just so many reactions out there that you couldn't tabulate that much. It's more efficient to tabulate the enthalpies of formation for different compounds, and then to use Hess's law to combine those enthalpies of formation so that you can calculate the enthalpy of reaction for any reaction that you want. And so here's the conceptual scheme. We are going to break our overall reactants to products, into two conceptual steps. We'll take our reactants and we'll decompose them into the elements in their reference forms. And then in the second step, we're going to recombine the elements to make the products. So step one is the reverse of a formation reaction. I should say it's the reverse of a set of formation reactions. And so the enthalpy of reaction for this first step, this delta H1, is a sum over the enthalpies of formation for all of the reactants, multiplied by their stoichiometric coefficients in the chemical equation, and then multiplied by 1 to account for the fact that this is a formation reaction in reverse. Okay, so this is the delta H for the first step. It's a sum over all of the reactants. There's a minus sign out in front, and then you multiply each delta H value, each enthalpy of formation, by the stoichiometric coefficients appearing in the chemical equation. For the second step, however, this is a formation reaction, or a set of formation reactions in the forward direction. So the enthalpy of reaction for step 2 is a sum over all of the products' enthalpies of formation multiplied by their stoichiometric coefficients in the chemical equation. Now, to get the overall delta H, the enthalpy of reaction for going from the reactants to the products, we need to add together the delta H's for the two steps. And so that leads to this products minus reactants formula for calculating the enthalpy of reaction. It may look a little complicated, but as you'll see when we start going through the examples, it's pretty easy to deal with. You just want to remember products minus reactants for calculating delta H values. The last thing I wanted to point out before we jump into the problems, in your textbook, okay, in the appendix here, appendix G, you see it's standard thermodynamic properties for selected substances. So these enthalpies of formation that I'm going to be using in the problems, they come from this table. So here for aluminum gas, here's the enthalpy of formation for aluminum gas. A whole bunch of different compounds. The enthalpy of formation is listed. Okay, so this is where those numbers are coming from. They're coming from Appendix G of the textbook. All right, so let's work some of these problems. So here we're being asked to calculate the enthalpy of vaporization of carbon disulfide using the enthalpies of formation, which we looked up in the thermodynamic table. So vaporization would be going from carbon disulfide liquid to carbon disulfide gas. And here's how you set up the delta H calculation. The enthalpy of this particular reaction is going to be the enthalpy of formation of all of the products. In this case, we have one product, and it's the carbon disulfide gas, minus the enthalpy of formation of all of the reactants. In this case, it's the carbon disulfide liquid. So we look these numbers up on the table and plug them in. So for the gas, we have 116.9 minus the 89.7 for the liquid. And we get 27.2, and that's going to be kilojoules per mole. Notice that the units of the enthalpy of formation are kilojoules per mole. So here's the simple one with just one reactant and one product. Let's look at another problem. This one's also vaporization, so I'm going to skip this one. Let's look at this reaction here. So we've got ammonia reacting with oxygen, platinum catalyst to produce nitrogen monoxide and water vapor. Calculate the enthalpy change from the thermochemical data, the enthalpies of formation. So I'm going to write out the enthalpy of reaction. We're going to start with the products. So we're going to need to take 4 times the enthalpy of formation of the nitrogen monoxide gas. Right? Why 4? Because the stoichiometric coefficient is 4. We have a second product. We're going to need to take plus 6 times the enthalpy of formation for the H2O gas. Now we're ready to start subtracting off the reactants. So I'm going to take minus 4 times, make it minus 4 times the enthalpy of formation for the ammonia, and then minus 5 times the enthalpy of formation for the O2 gas. Okay. Now, O2 gas is the reference form for oxygen, and so it has a value of 0. In fact, it'll probably be listed in the table as such, but oftentimes the value of the enthalpy of formation of the reference form of an element won't be listed at all. As you can see here, I didn't even include it because everyone should know that O2 gas has an enthalpy of formation value of 0. Anyway, so we'll plug in the numbers that we do have. So 4 times the number for nitrogen monoxide, plus 6 times the number for water vapor, minus 4 times the number for ammonia, and then we're going to run this through our calculator. And so I'm getting minus 906.0 kilojoules per mole. I'm going to check that number again. Yeah, I got the same value. So that's how you calculate these enthalpies of reaction in terms of the enthalpies of formation. Let's do this one, and I'll leave this exercise for you guys to try. So one more. The enthalpy of reaction for this one is going to be 2 times the enthalpy of formation for the nitric acid, plus the enthalpy of formation for the nitrogen monoxide gas. Now we can subtract off the reactants. So minus 3 times the enthalpy of formation for NO2 minus the enthalpy of formation for H2O liquid. Okay, and so we'll enter in the numbers from the table. So 2 times minus 207.4 plus 90.29 let's see, NO2 33.10 minus that negative 285.8. And so we'll run these through our calculator. And I'm getting minus 138.0. And that would be kilojoules per mole. I'll let you go ahead and check my number, and I'm going to go ahead and stop this video right here. We'll pick up with the next chapter in the next one.